In this video, I will derive for you in a very shortcut way a very famous equation which is called Bernoulli's equation. This equation relates three factors: kinetic energy, gravitational potential energy, and pressure. Let's draw first a cross-sectional area of a tube which has two ends. One is narrow, A1. The other end is wide, A2. And we assume a fluid, incompressible fluid, is moving from this end with a velocity of v1 towards the other end with a velocity of v2. The level here is y1, the level here is y2. The pressure here is P1, which is much more than the pressure here, P2, because the cross-sectional area here is less than the cross-sectional area here. Thus, the velocity here is more than the velocity there. The difference between the two heights is h, and here is the increase in y. If this incompressible fluid is static, or in other meaning standing still, then P1 minus P2 equals rho g y2 minus y1. And this equals rho g h. This term here reminds us with the gravitational potential energy, where the gravitational potential energy equals to mg h. If we divide the gravitational potential energy by a unit volume, then m over v is rho, which is the density of fluid. Therefore, P here is energy per unit volume. If this fluid is moving with v1 and v2 velocities, then it should have kinetic energy. The kinetic energy equals to half mv squared. If we divide this by unit volume, and this one by the unit volume, we will get m over v equals to rho. So it's half rho v squared. If we apply now the law of conservation of energy, we will have the sum of kinetic energy per unit volume and the gravitational potential energy per unit volume and the pressure, which is the energy per unit volume, equals to constant. And this is Bernoulli's equation. So Bernoulli's equation is half rho v squared plus rho Gy plus pressure equals to constant. And this would be Bernoulli's equation.